The Magic of Reality: How We Know What's Really True by Richard Dawkins, best-selling author of The Selfish Gene. Illustrated by Dave McKean. Richard Dawkins was told of this project at the National Press Club in Washington, D.C., September 30, 2013. Request for permission to reproduce this book in audio-visual format for YouTube was made to Free Press, and they've not yet replied. Coming soon, scientists reading the sciences and friends reading their introductions. Chapter 8. When and How Did Everything Begin? Let's start with an African myth from a Bantu tribe, the Bashango of the Congo. In the beginning, there was no land, just watery darkness, and also, importantly, the god Bomba. Bomba got a stomachache and vomited up the sun. Light from the sun dispelled the darkness, and heat from the sun dried up some of the water, leaving land. Bomba's stomachache still hadn't gone, though, so he then sucked up the moon, the stars, animals, and people. Many Chinese origin myths involve a character called Pangu, sometimes depicted as a giant hairy man with a dog's head. Here's one of the Pangu myths. In the beginning, there was no clear distinction between heaven and earth. It was all one gooey mess surrounding a big black egg. Curled up inside the egg was Pangu. Pangu slept inside the egg for 18,000 years. When he finally awoke, he wanted to escape, so he picked up his axe and hewed his way out. Some of the contents of the egg were heavy and sank to become the earth. Some of them were light and floated up to become the sky. The earth and the sky then swelled at a rate of the equivalent of 3 meters a day for another 18,000 years. Some versions of the story have Pangu pushing the sky and the earth apart, after which he was so exhausted that he died. Various bits of him then became the universe that we know. His breath became the wind, his voice became thunder, his 2 eyes became the moon and the sun. His muscles farmland and his veins roads. His sweat became rain and his hairs became stars. Humans are descended from the fleas and lice that once lived on his body. By the way, the story of Pangu pushing the sky and the earth apart is rather like the probably unrelated Greek myth of Atlas, who also held up the sky, although, weirdly, pictures and statues usually show him carrying the whole earth on his shoulders. Now here is one of many origin myths from India. Before the beginning of time, there was a great dark ocean of nothingness with a giant snake coiled up on the surface. Sleeping in the coils of the snake was Lord Vishnu. Eventually, Lord Vishnu was awakened by a deep humming sound from the bottom of the ocean of nothingness, and a lotus plant grew out of his navel. In the middle of the lotus flowers sat Brahma, Vishnu's servant. Vishnu commanded Brahma to create the world. So Brahma did just that. No problem. And all living creatures too, while he was about it. Easy. What I find a little disappointing about all these origin myths is that they begin by assuming the existence of some kind of living creature before the universe itself came into being. Bumba, or Brahma, or Pangu, or Unkalukakulu, the Zulu creator, or Abasi, Nigeria, or Old Man in the Sky, Salish, a tribe of Native Americans from Canada. Wouldn't you think that a universe of some kind would have to come first to provide a place for the creative spirit to go to work? None of the myths gives any explanation for how the creator of the universe himself, and it usually is a he, came into existence. So they don't get us very far. Let's turn instead to what we know of the true story of how the universe began. How did everything begin really? Do you remember from chapter 1 that scientists work by setting up models of how the real world might be? They then test each model by using it to make predictions of things that we ought to see, or measurements that we ought to be able to make, if the model were correct. In the middle of the 20th century, there were two competing models of how the universe came into being, called the steady state model and the Big Bang model. The steady state model was very elegant, but eventually turned out to be wrong. That is, predictions based on it were shown to be false. According to the steady state model, there never was a beginning. The universe had always existed in pretty much its present form. The Big Bang model, on the other hand, suggested that the universe began at a definite moment in time in a strange kind of explosion. The predictions made on the basis of the Big Bang model keep turning out to be right, and so it has now been generally accepted by most scientists. According to the modern version of the Big Bang model, the entire observable universe exploded into existence between 13 and 14 billion years ago. Why do I say observable? The observable universe means everything for which we have any evidence at all. It is possible that there are other universes that are inaccessible to all our senses and instruments. Some scientists speculate, perhaps fancifully, that there may be a multiverse, a bubbling foam of universes, of which our universe is only one bubble. Or it may be that the observable universe, the universe in which we live, and the only universe for which we have direct evidence, is the only universe there is. Either way, in this chapter, I am limiting myself to the observable universe. The observable universe seems to have begun in the Big Bang, and this remarkable event happened just under 14 billion years ago. Some scientists will tell you that time itself began in the Big Bang, and we should no more ask what happened before the Big Bang than we should ask what is north of the North Pole. You don't understand that? Nor do I. But I do understand, sort of, the evidence that the Big Bang happened and when. That is what this chapter is about. First, I need to explain what a galaxy is. We've already seen in our analogy with footballs in Chapter 6 that the stars are spaced out at incredibly huge distances from one another compared with the planets orbiting our sun. But vastly spaced out as they are, the stars are still actually clustered together into groups, and these groups are called galaxies. Here's a picture of 4 galaxies. Each galaxy shows up as a white swirling pattern that is actually made up of billions of stars and also clouds of dust and gas. Our sun is just one of the stars that make up the particular galaxy called the Milky Way. It is called that because on dark nights we get an end-on view of part of it. We see it as a mysterious streak or path of white across the sky, which you might mistake for a long, wispy cloud until you realize what it really is. And when you do, the thought should strike you dumb with awe. Since we are in the Milky Way galaxy, we can never see it in its full glory, but above is an artist's impression of it as if seen from outside, with our own position marked. It is marked as sun because on this scale there is no noticeable distance between the sun and any of its planets. And now here is a picture right. not an artist's impression, but an actual photograph taken through a telescope of hundreds of galaxies, each one a huge cluster of billions of stars, just like our Milky Way. I can't help being amazed every time I look at this that each one of those little smudges of light is an entire galaxy, comparable to the Milky Way. But that is the bare fact. The universe, our observable universe, is a very big place. The next important point is this. It is possible to measure how far away from us each galaxy is. How? How, for that matter, do we know how far away anything in the universe is? For nearby stars, the best method uses something called parallax. Hold your finger up in front of your face and look at it with your left eye closed. Now open your left eye and close your right. Keep switching eyes and you'll notice that the apparent position of your finger hops from side to side. That is because of the difference between the viewpoints of your two eyes. Move your finger nearer and the hops will become greater. Move your finger further away and the hops become smaller. All you need to know is how far apart your eyes are, and you can calculate this distance from eyes to finger by the size of the hops. That is the parallax method of estimating distances. Now, instead of looking at your finger, look at a star out in the night sky, switching from eye to eye. The star won't hop at all. It is much too far away. In order to make a star hop from side to side, your eyes would need to be millions of miles apart. How can we achieve the same effect as switching eyes millions of miles apart? We can make use of the fact that the Earth's orbit around the Sun has a diameter of 186 million miles. We measure the position of a nearby star against a background of other stars. Then, 6 months later, when the Earth is 186 million miles away, at the opposite side of its orbit, we measure the apparent position of the star again. If the star is quite close, its apparent position will have hopped. From the length of the hop, it is easy to calculate how far away the star is. Unfortunately, though, the parallax method works only for nearby stars. For distant stars, and certainly for other galaxies, our two alternating eyes would need to be much further apart than 186 million miles. We have to find another method. You might think you could do it by measuring how brightly the galaxy seems to shine. Surely a more distant galaxy should be dimmer than a closer one. The trouble is that the two galaxies might really be of different brightnesses. It's like estimating how far away a lit candle is. If some candles are brighter than others, how would you know whether you were looking at a bright candle far away or a dim candle nearby? Fortunately, astronomers have evidence that certain special kinds of stars are what they call standard candles. They understand enough of what is going on in these stars to know how bright they are, not as we see them, but their actual brightness, the intensity of the light, or it might be X-rays or some other kind of radiation that we can measure before it starts its long journey to our telescopes. They also know how to identify these special candles, and so, as long as they can find at least one of them in a galaxy, astronomers can use it with the assistance of well-established mathematical calculations to estimate how far away the galaxy is. So we have the parallax method for measuring very short distances, and there is a ladder of various kinds of standard candles that we can use for measuring a range of increasingly great distances, stretching out even to very distant galaxies. Rainbows and redshift. Okay, so now we know what a galaxy is and how to find out its distance from us. For the next step in the argument, we need to make use of the light spectrum, which we met in Chapter 7 on the rainbow. I was once asked to contribute a paper to a book in which scientists were invited to nominate the most important invention ever. It was fun, but I had left it rather late before joining the party, and all the obvious inventions had already been taken. The wheel, the printing press, the telephone, the computer, and so on. So I chose an instrument that I was pretty sure nobody else would choose, and is certainly very important even though not many people have ever used one, and I must confess that I've never used one myself. I chose the spectroscope. A spectroscope is a rainbow machine. If it is attached to a telescope, it takes the light from one particular star or galaxy and spreads it out as a spectrum, just as Newton did with his prism. But it is more sophisticated than Newton's prism because it allows you to make exact measurements along the spread out spectrum of starlight. Measurements of what? What is there to measure in a rainbow? Well, this is where it starts to get really interesting. The light from different stars produces rainbows that are different in very particular ways, and this can tell us a lot about the stars. Does this mean that starlight has a whole variety of strange new colors, colors that we never see on Earth? No, definitely not. You have already seen on Earth all the colors that your eyes are capable of seeing. Do you find that disappointing? I did when I first understood it. When I was a child, I used to love Hugh Lofting's Dr. Dolittle books. In one of the books, the doctor flies to the moon and is enchanted to behold a completely new range of colors, never before seen by human eyes. I loved this thought. For me, it stood for the exciting idea that our own familiar Earth may not be typical of everything in the universe. Unfortunately, though the idea is worthwhile, the story was not true, could not be true. That follows from Newton's discovery that the colors we see are all contained in white light and are all revealed when white light is spread out by a prism. There are no colors outside the range we are used to. Artists may come up with any number of different tints and shades, but all these are combinations of those basic component colors of white light. The colors we see inside our heads are really just labels made up by the brain to identify light of different wavelengths. We've already encountered the complete range of wavelengths here on Earth. Neither the moon nor the stars have any surprises to offer in the color department. Alas. So what did I mean when I said that different stars produce different rainbows with differences we can measure using a spectroscope? Well, it turns out that when starlight is splayed out by a spectroscope, strange patterns of thin black lines appear in very particular places along the spectrum. Or sometimes the lines are not black, but colored, and the background is black, a difference that I'll explain in a moment. The pattern of lines looks like a barcode, the sort of barcode you see on things you buy in shops to identify them at the cash till. Different stars have the same rainbow, but different patterns of lines across it. And this pattern really is a kind of barcode because it tells us a lot about the star and what it is made of. It isn't only starlight that shows the barcode lines. Lights on Earth do so too, so we've been able to investigate in the laboratory what makes them. And what makes the barcodes, it turns out, is different elements. Sodium, for example, has prominent lines in the yellow part of the spectrum. Sodium light, produced by an electric arc in sodium vapor, glows yellow. The reason for this is understood by physical scientists, but not by me because I'm a biological scientist who doesn't understand quantum theory. When I went to school in the city of Salisbury in southern England, I remember being utterly fascinated by the weird sight of my bright red skull cap in the yellow light of the street lamps. It didn't look red anymore, but a yellowish brown. So did the bright red double-decker buses. The reason was this. Like many other English towns in those days, Salisbury used sodium vapor lamps for its street lights. These give off light only in the narrow regions of the spectrum covered by sodium's characteristic lines, and by far the brightest of sodium's lines are in the yellow. To all intents and purposes, sodium lights glow with a pure yellow light, very different from the white of sunlight or the vaguely yellowish light of an ordinary electric bulb. Since there was virtually no red at all in the light supplied by the sodium lamps, no red light could be reflected from my cap. If you are wondering what makes a cap or a bus red in the first place, the answer is that the molecules of dye or paint absorb most of the light of all colors except red. So in white light, which contains all wavelengths, mostly red light is reflected. Under sodium vapor street lamps, there is no red light to be reflected, hence the yellowy brown color. Sodium is just one example. You'll remember from chapter 4 that every element has its own unique atomic number, which is the number of protons in its nucleus, and also the number of electrons orbiting it. Well, for reasons connected with the orbits of its electrons, every element also has its own unique effect upon light, unique like a barcode. In fact, a barcode is pretty much what the pattern of lines in the spectrum of starlight is. You can tell which of the 92 naturally occurring elements are present in a star by spreading the star's light out in a spectroscope and looking at the barcode lines in the spectrum. There's a website where you can choose any element you like and look at its spectral barcode. http://bit.ly/magic-of-reality-2, the numeral 2. Just move the slider along until you come to the element you want. They are arranged in order of atomic number from hydrogen upwards. For example, above is the picture for hydrogen, element 1, because it has only one proton, you'll remember. You can see that hydrogen produces 4 bars, one in the violet part of the spectrum, one in the dark blue, one in the pale blue, and one in the red. The wavelengths of the different colors are given at the top. In order to understand the pictures on this website, we need to be clear about a pair of otherwise confusing details. First, notice the 2 ways in which the bars appear, as colored lines on a black background in the upper part of the picture, and as black lines on a colored background in the lower part of the picture. These are called the emission spectrum, colored on black background, and the absorption spectrum, black on colored background. Which you get depends upon whether the element concerned is glowing with light, as when the element sodium glows in a sodium street lamp, or is getting in the way of light, as is often the case when an element is present in a star. I'm not going to bother with this distinction. The important point is that the bars appear in the same places along the spectrum in both cases. The barcode pattern is the same for any particular element, whether the lines are black or colored. The other complicating detail is that some bars are much more prominent than others. When looking at the light from a star with a spectroscope, we usually see only the very prominent bars. But that website gives all of the lines, including the faint ones that may be seen in the lab but don't usually show up in starlight. Sodium is a good example. For practical purposes, sodium light is yellow and its prominent bars appear in the yellow part of the spectrum. You can forget the other bars, although it's interesting that they are there, as they make the patterns look even more like barcodes. Here's the emission spectrum of sodium, with only the 3 strongest barcode lines shown. You can see how yellow dominates. So, Since every element has a different barcode pattern, we can look at the light from any star and see which elements are present in that star. Admittedly, it is quite tricky because the barcodes of several different elements are likely to be muddled up together. But there are ways of sorting them out. What a wonderful tool the spectroscope is. It gets even better. The sodium spectrum at the bottom of the page opposite is what you see if you look at the light from a Salisbury street lamp or from a star that is not very far away. Most of the stars we see, for example, the stars in the well-known constellations of the zodiac, are in our own galaxy. And the picture shown here of the spectrum of sodium light is what you see if you look at any of those. But if you look at the sodium spectrum from a star in a different galaxy, you get a fascinatingly different picture. At the top of this page is the barcode pattern of sodium light from 3 different places: on Earth or from a nearby star, from a distant star in a nearby galaxy, and from a very distant galaxy. Look first at the barcode pattern of sodium light from the distant galaxy, the bottom image, and compare it with the barcode produced by sodium light on Earth, the top image. You can see the same pattern of bars spaced the same distance from each other, but the whole pattern is shifted towards the red end of the spectrum. How do we know it is still sodium then? The answer is because the pattern of spacing between the bars is the same. That might not seem totally convincing if it only happened with sodium. But the same thing happens with all the elements. In every case, we see the same spacing pattern, characteristic of the element concerned, but shifted bodily along the spectrum towards the red end. What's more, for any given galaxy, all the barcodes are shifted the same distance along the spectrum. If you look at the middle image showing the sodium barcode in light from a galaxy that is somewhat close to ours, closer than the very distant galaxies I talked about in the previous paragraph, but further away than the stars in our own Milky Way galaxy, you see an intermediate shift. You see the same spacing pattern, which is the signature of sodium, but not shifted so far. The first line is shifted along the spectrum away from deep blue, but not as far as green, only as far as light blue. And the 2 lines in the yellow, which combine to make the yellow color of the Salisbury street lamps, are both shifted in the same direction, towards the red end of the spectrum, but not all the way into the red as they are in light from the distant galaxy, only a little way into the orange. Sodium is just one example. Any other element shows the same shift along the spectrum in the red direction. The more distant the galaxy, the greater the shift towards the red. This is called the Hubble shift because it was discovered by the great American astronomer Edwin Hubble, who also gave his name after his death to the Hubble telescope, which was used, incidentally, to photograph the very distant galaxies shown on page 167. It is also called a red shift because the shift is along the spectrum in the direction of red. Backwards to the Big Bang. What does the red shift mean? Fortunately, scientists understand it well. It is an example of what is called a Doppler shift. Doppler shifts can happen wherever we have waves, and light, as we saw in the previous chapter, consists of waves. It's often called the Doppler effect, and it is more familiar to us from sound waves. When you are standing at a roadside watching the cars whiz by at high speed, the sound of every car's engine seems to drop in pitch as it passes you. You know the car's engine note really stays the same, so why does the pitch seem to drop? The answer is the Doppler shift, and the explanation for it is as follows. Sound travels through the air as waves of changing air pressure. When you listen to the note of a car engine, or let's say a trumpet, because it is more pleasant than an engine, Sound waves travel through the air in all directions from the source of the sound. Your ear happens to lie in one of those directions. It picks up the changes in air pressure produced by the trumpet, and your brain hears them as sound. Don't imagine molecules of air flowing from the trumpet all the way to your ear. It isn't like that at all. That would be a wind, and winds travel in one direction only, whereas sound waves travel outwards in all directions, like the waves on the surface of a pond when you drop a pebble in. The easiest kind of wave to understand is the so-called Mexican wave above, in which people in a large sports stadium stand up and then sit down again in order, each person doing so immediately after the person on one side of them, say their left side. A wave of standing and then sitting moves swiftly around the stadium. Nobody actually moves from their place, yet the wave travels. Indeed, the wave travels far faster than anybody could run. What travels in the pond is a wave of changing height in the surface of the water. The thing that makes it a wave is that the water molecules themselves are not rushing outwards from the pebble. The water molecules are just going up and down, like the people in the stadium. Nothing really travels outwards from the pebble. It only looks like that because the high points and low points of the water move outwards. Sound waves are a bit different. What travels in the case of sound is a wave of changing air pressure. The air molecules move a little bit to and fro, away from the trumpet, or whatever is the source of the sound, and back again. And they do so. They knock against neighboring air molecules and set them moving backwards and forwards too. Those in turn knock against their neighbors, and the result is that a wave of molecule knocking, which amounts to a wave of changing pressure, travels outwards from the trumpet in all directions. And it is the wave that travels from the trumpet to your ear, not the air molecules themselves. The wave travels at a fixed speed regardless of whether the source of the sound is a trumpet or a speaking voice or a car. About 768 miles per hour in air, 4 times faster underwater, and even faster in some solids. If you play a higher note on your trumpet, the speed at which the waves travel remains the same, but the distance between the wave crests, the wavelength, becomes shorter. Play a low note and the wave crests space out more, but the wave still travels at the same speed. So high notes have a shorter wavelength than low ones. That is what sound waves are. Now for the Doppler shift. Imagine that a trumpeter standing on a snow-covered hillside plays a long, sustained note. You get on a toboggan and speed past the trumpeter. I chose a toboggan rather than a car because it is quiet so you can hear the trumpet. What will you hear? The successive wave crests leave the trumpet at a definite distance from each other, defined by the note the trumpeter chose to play. But when you are whizzing towards the trumpeter, your ear will gobble up the successive wave crests at a higher rate than if you were standing still on the hilltop. So the trumpet's note will sound higher than it really is. Then, after you have whizzed past the trumpeter, your ear will hit the successive wave crests at a lower rate. They'll seem more spaced out because each wave crest is traveling in the same direction as your toboggan. So the apparent pitch of the note will be lower than it really is. The same thing works if your ear is still and the source of the sound moves. It is said, I don't know whether it is true, but it is a nice story, that Christian Doppler, the Austrian scientist who discovered the effect, hired a brass band to play on an open railway truck in order to demonstrate it. The tune the band was playing suddenly dropped into a lower key as the train puffed past the amazed audience. Light waves are different again. Not really like a Mexican wave, and not really like sound waves. But they do have their own version of the Doppler effect. Remember that the red end of the spectrum has a longer wavelength than the blue end, with green in the middle? Suppose the bandsmen on Christian Doppler's railway truck are all wearing yellow uniforms. As the train speeds towards you, your eyes gobble up the wave crests at a faster rate than they would if the train was still. So there is a slight shift in the color of the uniform towards the green part of the spectrum. Now, when the train goes past you and is speeding away from you, the opposite happens, and the band uniforms appear slightly redder. There's only one thing wrong with this illustration. In order for you to notice the blue shift or the red shift, the train would have to be traveling at millions of miles per hour. Trains don't travel anywhere near fast enough for the Doppler effect on color to be noticed. But galaxies do. The shift of the spectrum towards the red end, which you can clearly see in the positions of the sodium barcode lines in the picture on page 172, shows that very distant galaxies are traveling away from us at a rate of hundreds of millions of miles per hour. And the more distant they are, as measured by the standard candles that I mentioned above, the faster they are traveling away from us, the greater the red shift. All the galaxies in the universe are rushing away from each other, which means that they are rushing away from us too. It doesn't matter which direction you point your telescope in, the more distant galaxies are moving away from us and from one another at ever-increasing speed. The entire universe, space itself, is expanding at a colossal rate. In that case, you might ask, why is it only at the level of galaxies that space is seen to expand? Why don't the stars within a galaxy rush away from each other? Why aren't you and I rushing away from each other? The answer is that clusters of things that are close to each other, like everything in a galaxy, feel the strongest pull from the gravity of their neighbors. This holds them together, while distant objects, other galaxies, recede with the expansion of the universe. And now, here is something amazing. Astronomers have looked at the expansion and worked backwards through time. It is as though they constructed a movie of the expanding universe with the galaxies rushing apart and then ran the film in reverse. Instead of hurtling away from each other, in the backwards film the galaxies converge. And from that film, the astronomers can calculate back to the moment when the expansion of the universe must have begun. They can even calculate when that moment was. That's how they know it was somewhere between 13 and 14 billion years ago. That was the moment when the universe itself began, the moment called the Big Bang. Today's models of the universe assume that it wasn't only the universe that began with the Big Bang. Time itself and space itself began with the Big Bang too. Don't ask me to explain that because, not being a cosmologist, I don't understand it myself. But perhaps you can now see why I nominated the spectroscope as one of the most important inventions ever. Rainbows are not just beautiful to look at. In a way, they tell us when everything began, including time and space. I think that makes the rainbow even more beautiful. Disappointing about all these origin myths is that they begin by assuming the existence of some kind of living creature before the universe itself came into being. Bumba or Brahma or Pangu or Unkalukakulu, the Zulu creator, or Abasi, Nigeria, or Old Man in the Sky, Salish, a tribe of Native Americans from Canada. Wouldn't you think that a universe of some kind would have to come first to provide a place for the creative spirit to go to work? None of the myths gives any explanation for how the creator of the universe himself, and it usually is a he, came into existence. so they don't get us very far. Let's turn instead to what we know of the true story of how the universe began. How did everything begin, really? Do you remember from Chapter 1 that scientists work by setting up models of how the real world might end years? When he finally awoke, he wanted to escape, so he picked up his axe and hewed his way out. Some of the contents of the egg were heavy and sank to become the earth. Some of them were light and floated up to become the sky. The earth and the sky then swelled at a rate of the equivalent of 3 meters a day for another 18,000 years. Some versions of the story have Pangu pushing the sky and the earth apart, after which he was so exhausted that he died. Various bits of him then became the universe that we know. His breath became the wind, his voice became thunder, his 2 eyes became the moon and the sun, his muscles farmland and his veins roads. His sweat became rain and his hairs became stars. Humans are descended from the fleas and lice that once lived on his body. By the way, the story The Magic of Reality, How We Know What's Really True, by Richard Dawkins, best-selling author of The Selfish Gene, illustrated by Dave McKean. Richard Dawkins was told of this project at the National Press Club in Washington, D.C., September 30, 2013. Request for permission to reproduce this book in audio-visual format for YouTube was made to Free Press, and they've not yet replied. Coming soon, scientists reading the sciences and friends reading their introductions. Chapter 8. When and how did everything begin? The story of Pangu pushing the sky and the earth apart is rather like the probably unrelated Greek myth of Atlas, who also held up the sky, although, weirdly, pictures and statues usually show him carrying the whole earth on his shoulders. Now here is one of many origin myths from India. Before the beginning of time, there was a great dark ocean of nothingness with a giant snake coiled up on the surface. Sleeping in the coils of the snake was Lord Vishnu. Eventually, Lord Vishnu was awakened by a deep humming sound from the bottom of the ocean of nothingness, and a lotus plant grew out of his navel. In the middle of the lotus flowers sat Brahma, Vishnu's servant. Vishnu commanded Brahma to create the world. So Brahma did just that. No problem. And all living creatures too, while he was about it. Easy. What I find a little Let's start with an African myth from a Bantu tribe, the Bashango of the Congo. In the beginning, there was no land, just watery darkness, and also, importantly, the god Bomba. Bomba got a stomachache and vomited up the sun. Light from the sun dispelled the darkness, and heat from the sun dried up some of the water, leaving land. Bumba's stomachache still hadn't gone, though, so he then sucked up the moon, the stars, animals, and people. Many Chinese origin myths involve a character called Pangu, sometimes depicted as a giant hairy man with a dog's head. Here's one of the Pangu myths. In the beginning, there was no clear distinction between heaven and earth. It was all one gooey mess surrounding a big black egg. Curled up inside the egg was Pangu. Pangu slept inside the egg for 18,000